In the name of Almighty God, I'm Master Sankoshi, and today I want to talk about the chemical reaction engineering module, and the section is Equilibria, that I want to have a literature about it. When one or more equilibrium reactions are present, the section which allows the user to enable mass-preserving initialization is shown. When enabled, the solver will first solve for the values of the species participating in an equilibrium reaction while disregarding any kinetic reactions. The solution to the equilibrium subproblem is then used as a consistent starting point for the time stepping. The functionality solves a log transport version of the problem, which in turn puts a requirement that a finished concentration is present for each building block, atom, kind, charge, and/or a combination therefore. If settings is changed from automatic to manual, the user may change the maximum number of iterations and the absolute tolerance. Now I want to go through the reaction. Use reaction node to implement a chemical reaction involving a number of chemical species. The participating species may represent any kind of molecular entities like atoms, molecules, ions, or radicals. To add a reaction node, either right-click to reaction engineering node or on the reaction engineering toolbar, click reaction. Now I want to go through the reaction formula. Enter chemical reaction equation. In the formula field, the chemical equation should be of the format A plus B arrow C plus D here. A and B are reactants and C and B are product species, and arrow denotes reaction arrow. The participating species should be written with valid species name. Valid reaction arrows are bidirectional for reversible reaction and one directional for irreversible reaction. And equality for equilibrium reaction species can be given tribal names, or their chemical formulas can be used as names. Examples of valid formulas are carbon plus oxygen, reversible as a irreversible and one directional carbon dioxide. And the better, in other words, we can say that the carbon as a solid plus oxygen as a gases in a one directional or irreversible direction or equation. They have a carbon dioxide as a gases. Click apply to let the interface parse the reaction. This process identifies the participating species as well as its stoichiometric coefficients and any charge of ionic species. The species feature is automatically added for all participating species. Balance. The balance button to automatically calculate the stoichiometric coefficients such that the number of atoms of each kind are the same on both sides of the reaction. This tells, for example, the formula hydrogen oxygen one directional is water into the two atoms of the hydrogen, one oxygen will be given the two atoms of the water. The balancing involves parsing all participating species for elements in the periodic table. It therefore requires that all species in the formula field are written either using their chemical formula, say H2O, or that the species in this reaction have an enabled chemical formula field in their species node. For example, it is possible to balance the formula H2 plus O2 will be given water as long as there is species node with the name water all present and an enabled chemical formula. For automatic reaction balancing to be successful requires that the problem is well posed. One example of a problem that is not well posed is carbon plus hydrogen will given the CH4 or C2H6, in which case any ratio of CH4 C2H6 could be obtained. Another example is H2 one directional, which is given the oxygen where not all elements are present on both sides. Reaction type. Select a reaction type: reversible, irreversible, or equilibrium, or edit the expression directly in the formula field. In the latter case, specify the reaction type with a delimiter space separating the two sides of the equation. Bidirectional denotes a reversible reaction, one directional denotes an irreversible reaction, and equality denotes a reaction at chemical equilibrium. Each reaction type has its own set of reaction kinetics. When the reaction is reversible or irreversible, the rate of reaction rate J for reaction J contributes to change in species I in the manner of the Ri is equal to sigma. The lower boundary is J, Vi, J, where Rj, where Vij is a stoichiometric coefficient. In the case of the an equilibrium reaction, the equilibrium expression is equal to the equilibrium constant. Chi equality is equal to chi equality zero. Reaction rate. This section is available when the reaction type is either reversible or irreversible. When mass action allows is selected default, the rate expression is automatically derived from the stoichiometric coefficients in the reaction formula. For the irreversible reaction type, the reaction rate becomes Rj is equal to Kj to the power of F multiplication, and the lower boundary I belongs to the reactant Ci to the power of minus Vij. For the reversible reaction type, the expression instead becomes Rj is equal to Rj to the power of k, which is given chi j to the power of chi multiplication I to belongs to reactant Ci to the power of minus Vij minus chi j to the power of R multiplication I belongs to production Ci to the power of Vij. The deduced or reaction order is shown in the text below the respective equation in the reaction rate section. Now I want to go to the arbitrary rate expression. If the reaction order differs from the stoichiometric coefficients, or if an arbitrary rate expression is applicable, change reaction rate to user-defined expression field or appears with the default expression. Be that from the mass action law below this, there are fields to set the reaction order. For a reversible reaction, the reverse reaction order may be specified in addition to the forward one. The unit of the rate constant K or frequency factor R in the case of the Arrhenius behavior is derived from the reaction order in the SI units cubic meter per molar to the power of alpha minus 1 per second, where alpha equals the order with respect to the volumetric species. When surface species are present, identified by their ADS suffix, the unit is instead given by the m to the power of 3 alpha plus 2 beta minus 2 divided by molar to the power of alpha plus beta minus 1 per second, where beta is the order with respect to the surface species considered. For example, the reaction 2H2O4 to the power of minus 2 plus H2O, which is given as 2O3 to the power of minus 2 plus 2HSO3 minus. Automatically, the used reaction order is 3. However, in the case that the water is solvent, the order should probably be 2. This is specified as follows. Figure 2-5 illustrates the reaction order can be manually specified for a user-defined reaction rate. Now I want to go to the rate constants. This section applies for reversible or irreversible sections reactions and defines the reaction rate constants used in the reaction rates. Forward rate constant and reverse rate constant. The forward rate constant K to the power of F is used for both reversible and irreversible reactions. The reverse rate constant K to the power of R is only used for reversible reaction. Equation 2-86. The SI units of the rate constant are automatically based on the order of the reaction with respect to the concentrations as defined in the reaction formula. Now I want to go to the specified equilibrium constant. The specified equilibrium constant checkbox is available for reversible reaction if the checkbox is selected. The rate constant are defined in a different manner, with the reverse rate constant being computed from the following expression. K to the power of F is equal to K to the power of F divided by K equal to 0. Thus, in this case, the forward rate constant and equilibrium constant for the reaction are needed. The equilibrium constant is edited in the equilibrium settings section. Thank you so much for watching my tutorial video until the end. Today is the 7th of May 2026. Time is 5:42 a.m.